Welcome. In this video, I want to do a couple of examples of additional problems with lens and mirror. Partly to show you some new techniques and partly to show you some mistakes that to avoid. Let's begin. Now, this is actually similar to things you've done before, but we can reverse the problem. Previously, I was showing you how to find the image. Now we're going to start with the image. Here we have a concave mirror. It's a large one, the focal length of 60 centimeters. And what we see is the image of a tree in front of the mirror. Now, this is a realistic kind of experiment. If you took a large concave mirror, I mean the 60 centimeter is the focal length, but I'm assuming it's also large in size. It's not a miniature mirror. A large mirror can gather a lot of light. So if you kind of point that mirror at an object, it will gather enough light. It's a large. When I say a large mirror, I mean, like if you held it in your hands, you're maybe a couple of feet between your two hands, like a diameter of a couple of feet, but the focal length is 60 centimeters. So this mirror, you gather enough light, you're pointing at an object, that the image will be very visible. You can either put a piece of paper to the side of the mirror and see the image, or kind of tilt it to see the image on the wall. So in this case, what you see there, the image is a tree. It's inverted. That's why the tree is upside down. You see the light is coming from the right. Now if you look closely at those light rays, if you say they don't look exactly parallel, no, they're not parallel. The tree is not infinitely far away. It's far enough away that the rays are almost parallel. So light comes from the right to the mirror. The object is off to the right somewhere and forms an image. And there it's an inverted image. Now, what do we want to know? Well, we ask the question, how far is the tree? Say you're sitting in your room, you got this mirror, you point it out the window at a tree, and without leaving your room, just with this mirror, can you tell how far the tree is from the mirror? Can you tell how big is the tree? Again, you're sitting in your room, you have this big mirror, you point it out the window, you see the image of a tree. You, of course, will kind of move the mirror so that it's just the right distance, give you a sharp image on the wall, and you want to answer those two questions. How would you do it? Well, the first thing you do, measure the distance, d sub I, from the mirror to the image. In this case, we get 61 centimeters. It's a little larger than the focal length. A little larger because the object is far away. Remember, as the object gets very far away, the image gets very close to the focal point. We measure the size of the image, h sub I. Okay, here's one of the first mistakes you want to avoid. If you were to measure that image with a ruler has no negative numbers on it. You measure it, it's 4.7 centimeters on the ruler, but it's negative. Negative because you can see clearly the tree out of your window is, the green is on the top, the image, the green is on the bottom. Negative 4.7 centimeter h sub I. Now, with those the three pieces of information: the focal length of the mirror, d sub I, h sub I. When answer the two questions, how far is the tree and how big is the tree? Of course, we're talking about the object. We've measured the image. We want to learn something about the object. Okay, here's my whiteboard. There's the information: d sub I, h sub I, the focal length of the mirror. There's the mirror equation. Well, we plug in the values. So we have di is 61, f is 60. Now, both of these are centimeters, so I didn't have to change the unit. You solve that for do. The object is 3,660 centimeters from the mirror. Well, it's not convenient to talk about 3,000 centimeters. 100 centimeters is a meter. Therefore, we divide by 100. That tree is 36.6 meters from the mirror. 36.6 meters, something, of the order of 100 feet away. Now, I want to know how big is that tree. Here's the magnification equation. We know di, that's 61 centimeter. We solve for do, and in this case, because we want to keep the units the same, we're not going to plug 36 meters in there. We're going to stay with 3,660. It's not convenient to state a distance like that, but in this equation, we want the units to cancel out. Centimeter over centimeter, so we use the 3,660. Magnification minus 0.0167. Very tiny. You don't think of that as magnification, but that's the definition. Because the image you're looking at is much smaller than the actual tree. So you get a very small number. It's negative because it is a real image. It's inverted. Now, if that number equals hi over ho, we want to solve for ho. Well, you'd have to multiply both sides by ho, divide both sides by m. You find that ho is equal to hi over m minus 0.0167. So now we plug in the value. We know hi. Remember, we measured that. It's a negative number. We have a negative 4.7 centimeters over this negative magnification. The two negatives cancel. HO is 282 centimeters, or, more convenient, we'd say the tree is 2.8 meters high. So the tree is about 100 feet or so away, about 9 feet high. It's a typical small tree. So, different way to state a problem with a mirror. And also, it kind of illustrates something interesting you can do. If you had this big mirror, without leaving your room, you can find out how far away is the tree, how big is it, and maybe you learn something that's by doing the experiment. Now we want to look at different kind of problem. How do we solve a problem with two lenses? Very, very practical. Why? Well, a telescope has two lenses. A microscope has two lenses. Binoculars have two lenses. And guess what? What if you use a vision correction? Whether eyeglasses or contact lenses. Well, your eye has its own lens. You put a contact in front of it or eyeglasses in front of it, you have a two-lens problem. Very, very important problem. Very, very practical. How do we solve the two lens problem? We'll come back to this when we do vision correction. But for now, let's go over the rules for how we do this. The first rule, you don't lump the lenses together. You solve one lens at a time. The second rule, the image from the first lens, we're going to call the first lens A, capital A. The image from the first lens becomes the object for the second lens. We call the second lens capital B. The third rule, the overall magnification is the product, the magnification from the first lens, M sub A, times the magnification from the second lens, M sub B. Okay. If you need to pause the video, pause it, write down those three rules. So you have them on a piece of paper, you can look at them and refer to them as we solve the problem. Okay. Now, one little bit of preliminary information, here, going to help us to solve the problem. Here we have light is coming from the left. You see the light, the arrows on the left-hand side. The first lens is the lens where the light reaches first. That's going to be A. Focal length f sub A. When it passes through that lens, the next lens it comes to, the second lens we call B, focal length f sub B. The two lenses are separated by a distance d. We're going to use that definition or symbol d, the separation between the two lenses. When the light passes through that first lens, we'll form an image. Again, let's pretend it's a tree. The inverted tree you see right there is the image from the first lens. So if you solve that problem, if you knew how far away that object was from the first lens, you could solve for the image distance d sub I from the first lens. I'm going to call d sub I capital A. Distance of the image from lens A. Now this image from A becomes the object for B. That little tree is the image of the first lens, the object for the second lens. We consider the light from the image going to the second lens. We need to know what is, in order to solve that problem, what is the distance of that object from the second lens? We call it d sub O capital B. So, if you need to stop it, make a picture, make sure you know those variables, those definitions. The separation between the two lenses, d, image distance from A, d sub IA, the object distance to B, d sub O B. Now, what's d sub O B? Well, if you look at this picture, it should be apparent that d sub IA plus d sub OB are equal to d, the separation. Therefore, we're going to need to know the object distance to the second lens. D sub OB equals d minus d sub IA. That should be very evident from looking at the picture. Okay, I call that case 1. Let's consider, we could do many, many cases, but 2 cases will make the point. Let's consider case 2. Case 2, what we're going to do is we put the lenses much closer together. D is much smaller. We have the same object, the same F sub A, F sub B. So when that light passes through the first lens, makes its image is all the way over on the other side of that lens. Remember, if you back up the video, originally that image fell between the two lenses. We brought the two lenses closer. So the image from lens A is all the way on the other side of lens B. Now, D sub IA, the distance of that first image. Remember, this is not the final image, it's the image from the first lens, D sub IA. But I need to know, how can the light from that image go through the second lens? Well, we can solve the problem. We need to know what is D sub OB. Now you want to look at this a little bit, think about it, do some algebra. And you say, well, it looks like D plus D sub OB equal DIA. So one way to solve this problem would be to say, well, if I took D sub IA and subtracted D, I should get DOB. Except this image, which will be the object for lens B, the second lens, is on the far side, the thing of before and after side of the lens. It's on the after side of the lens. Therefore, this is the situation where D sub OB is negative. For the lens, if the object is in front, it's a positive D sub O. If the object is after the lens, it's a negative D sub O. So D sub OB is a negative value. Therefore, the answer is not DIA minus D, it's the negative of that. It's D minus DIA gives you DOB, which, if D is smaller than DIA, will be a negative number. Now, if you go back to your notes or back to the previous case 1, you'll say that's the same equation. In the first case, case 1, DOB equals D minus D sub IA, positive. For case 2, DOB equals D minus D sub IA, negative. The object for the second lens can be in front of it, can be after it. Okay. In either case, we use the same equation. That's what I wanted to illustrate from these two cases. The same equation to get D sub OB. All right. Now we've established that. Let's do a quantitative example. And I want to set it up as cells. DOB is 28 centimeter. We put in the 28 centimeter. FB, the focal length of the second lens, you go back to the problem, that's 15. Now I can solve for the image distance for the second lens. DIB 32.3. Now I solve for the magnification from the second lens. Again, I've added subscript B. Minus D sub IB over D sub OB. DIB 32.3. DOB, remember we carried that from the previous problem. That's the 28. So M sub B minus 1.15. The magnification from the second lens. Put a division on my whiteboard. I want to put some things together now. want to determine what is the overall magnification. Now, hopefully you wrote down some results from the first lens. We need that now. The product, m sub a times m sub b, given by these two numbers. If you need to go back, look at your notes, back up the video. M sub a was a virtual image of plus 0.20. Here's the second one, m sub b. That's a real inverted image, negative 1.15. That product. This is the overall magnification from the two lenses. An inverted image, negative 0.23. Therefore, the final image, this is HI. This is the thing you would see coming out of the two lens system. It's inverted. There's a negative 0.23 H sub O. So it's smaller than the object, like 0.23 times the object. It is inverted. That's the solution to the problem. If you didn't follow it, I recommend you watch this again, draw the picture, go through step by step. You will understand where every number came from, where every number went to. To summarize, I'm going to try to put some of this into words here. That's the same statement of the problem. We found d sub IB 32.3 centimeter. What is that? The image formed by the two lenses is a positive 32.3 centimeter after the second lens. You state that this number is relative to the second lens, the final lens in the system. If that had been a negative, it would have been before the second lens, but it's a positive. It's after the second lens. You have to state whether it's a positive or negative, whether it's before or after the final lens. This one is positive. It's going to be after the second lens. We found HI equals minus 0.23 HO. The overall magnification of the two lenses is negative 0.23. The image formed by the two lenses has a size which is negative 0.23 of the starting object. We had some intermediate steps. We had intermediate image and intermediate object. But at the end, we say, what's that object we started with? What's that image we got at the end? Here's the summary. Okay, that's the end of the video. I thank you for watching, for listening, for taking notes all the way to the end.